All right. We're going to start actually getting into the content here of chapter 12. We're going to cover most this week and the first half of next. Actually, between this week and the first half of next week, we will cover all of chapter 12. The nice thing is, though, that a good bit of it and a lot of what we're doing today will be review. But then obviously we're going to build on it, particularly in the area of dealing with three dimensions. Okay. We will also get into parametric equations, which you guys did a little of last year, in 2 dimensions, but we'll be working with that in 3 dimensions as well. Which, if you think about it, is really 4 dimensions, because you have 3-dimensional space and then the dimension of time thrown in there as well, with a parameter. So that's where we're building to here. But today's lesson, we're going to cover a lot of the basics about vectors, refresh our memories on some things, obviously learn some new things, but we're going to focus mostly today on vectors geometrically, visualizing them, understanding them visually, and understanding the concepts involved. And then tomorrow we'll get into more algebraic representation of vectors, which we'll start a little bit at the end of the day today. So, just starting out with a basic definition, and the difference between a scalar and a vector. All right, a scalar is just a number, a measurement. A vector is something that has both a measurement, a magnitude, but also has a direction indicated as well. All right, so whereas we might have a scalar of speed, when we indicate which direction we're traveling that speed, we have now a vector velocity. If we are dealing with pounds, we're just talking about pounds, or if you're in metrics, newtons. When we talk about what direction those pounds are pushing in, we're talking about a vector force, a vector of force. When we talk about distance, obviously that's just a scalar. But when we tell what direction we're going in that distance, we're talking about a displacement vector. And these aren't the only ones, but they are very, very common ones: velocity, force, and displacement. They're probably the most common ones you'll run into. If you studied physics, or if you are studying physics, you may have already dealt with some of this. You'll probably have learned it on a very practical level. Here we're going to get into more of the mathematics behind it, why it works, and all that. So that's kind of where we're heading. I want to review a little bit of notation and also point out some notation the book uses that you may not have seen before. There we go. Okay. A couple of ways to represent a vector. We could use a lowercase letter with this half arrow above it. Okay. You'll see people, even your book actually will write it with a full arrowhead. But technically the proper way is to write it with just a half arrow on the top. In printed text, you'll see just a lowercase letter in bold. Right? You cannot write in bold. I don't want you writing over the same letters 8 times or something and say that's bold, so it's a vector. When you're handwriting it, you'll use this notation most likely with the arrow. Or, and this is something your book has, but honestly I've never seen, but just in case you happen to see it in the future on an IB exam or something, the V with the little tilde above it is also notation for a vector. Okay. I'm not sure exactly where that's used, but I know it's in your book, and just so that if you see it, you know what it is. Okay? Now, you also have a vector from a point to another. And in that case, we would actually use those 2 points in the name of our vector. Okay? So vector AB starts at A and goes to B. So we would draw it like this. With an endpoint at A, we would draw the arrow up here at B, but I like to put the endpoint there as well, just so that I remember that this isn't like a ray in geometry where it keeps going forever past B. Right? There is direction, and that's why we have the arrow, but it does have a defined magnitude, and that is represented by the distance between A and B here. Okay? Now, obviously, A and B, this vector doesn't have to be a displacement. This doesn't have to be distance. But one of the things that using vectors allows us to do is it allows us to visualize things that aren't visible. Okay? You can't see a velocity. You can't see a force. All right? But by drawing these arrows and making them proportional to each other based on their magnitudes, we can visualize what's going on. And I would recommend when you guys make a sketch for a problem, try to draw them at least somewhat to scale. Okay, if you're dealing with forces and one force is 100 pounds and the other is 50, make the 50-pound vector half as long as the 100-pound vector. Okay? Also, if you're given angles, try to draw those angles as accurately as possible. You don't necessarily have to get out a protractor and measure it, but at least making it close will really help you as you try to figure out how to solve a particular problem. Okay? Some other notation, and we'll talk about how to find it algebraically later, but some other notation here is the magnitude. The magnitude of a vector, you'll notice this notation here, it looks like an absolute value, all right, but that indicates magnitude. Now, you may be asked to find the magnitude of a vector. Right? More often, however, you're going to be asked to find the magnitude indirectly. For example, they'll give you a situation with a number of different velocities, and they'll say, what is the resulting speed? Okay? Well, speed is the magnitude of the velocity vector. Okay? Or the pounds or newtons involved are the magnitude of the force. The distance we travel would be the magnitude of the displacement vector. So just keep that in mind as you're working on different problems. They may be asking for magnitude without actually using the term magnitude. Okay? Now, a couple other things here. Parallel vectors and equal vectors. Okay, parallel and equal. Understand the difference here. Parallel vectors have the same direction. They have the same direction. Notice the arrow would have to go the same way as well. Okay? If I had, this right here, but I had, that's why. Do this. There we go. Let's say I had my arrow go in the opposite direction. these would not be parallel. Okay, those would be opposing. They would actually be negative. Alright, so they do have to go the same direction, including the arrow. And that's something that's easy to make a mistake on. If the arrows are going opposite directions, we're thinking parallel lines. It's not the same idea. Okay? Now, equal vectors have to be parallel and have the same magnitude. Alright, so you'll notice these three up here have different lengths. These two down here have the same length, so those represent equal vectors because the magnitude is the same as well. So not a terribly difficult concept, but something we need to keep in mind as we're working through things. Okay. Now, what would the direction and magnitude of a zero vector be? Okay? In number theory, a lot of times one of the challenges when we're dealing with something other than just real numbers is to define what an identity would be, or what zero is in that case. You know, for example, if you guys ever study matrices, which we may do a little at the end of the year, you know, if you have a 3 by 3 matrix, the zero matrix is that, okay? That's zero. Alright, we have to define that. If I'm looking for the identity would be this. Okay? So, anytime in mathematics that we're dealing with some kind of in computers they call them a data structure or data type, but anytime we're dealing with something that's not just a real number, we have to make sure we define what zero is, what an identity is. So we have a zero vector. What do you think that might be?
Would it just be a point?
Yeah, it would just be a point. The point O. Okay, or what would the magnitude be?
No direction?
What?
No direction?
There's no direction defined here because it's just a point. What would the magnitude be then? Zero. All right, zero. Okay, there's no length there. There's zero. Okay, now you might say, well, what's the point of having a zero vector? Often, what we'll be using here in a zero vector is we'll be trying to find a balancing point. Okay, in fact, in physics, if any of you looking into going to engineering, a couple of you were, okay. If you go into engineering, most likely you'll have to take an entire course in what's called statics. Okay, statics is a branch of physics designed to study how to keep things balanced, basically how to get zero vectors. And actually the term static is the same as the literature term static. Okay, a static character is someone who through the whole story, what? Remains the same. Okay, so when we're dealing with statics, we're wanting something to stay the same. How do we get this part that's connected to these different parts to just stay where it is? Okay, or, you know, if we're building a bridge, how do we get the bridge not to fall? You know, we need to balance forces. You know, that, again, that's a whole branch of physics, as opposed to dynamics. Dynamics is studying how to use engineering to make things move the way you want them to, okay? So we have a 0 vector here. We can also deal with multiple vectors, okay? And this is what's known as scalar multiplication. I'm multiplying a vector by a scalar. Another thing in number theory, when you're talking about mathematics, you have to redefine operations. So, in dealing with vectors, there's actually 3 different types of multiplication. 2 we're actually going to talk about, the other one I'll mention, but we're not really going to use. Okay? We have scalar multiplication here, we have a dot product later on, and there's also something called a cross product. So there's 3 different kinds of multiplication when we're talking about vectors. But here, scalar multiplication is actually a relatively simple concept because we're just taking these vectors and putting them one right after another. Okay, so if this is vector v, then this right here would be 3 vector v. Okay, and you'll notice the direction will stay the same, but the magnitude is going to be multiplied. Alright, so if this is a 50-pound force, then this would be a 150-pound force. Okay? And this would be what you would end up with if, say, you had 3 identical things all pulling on the same object. You know, or if you have a boat with 3 engines on the back, you have one of those big racing boats or something that has 3 engines on the back, they're all pushing the same direction. So you have 3 times what one would do. Okay? But there we're dealing with multiple vectors. Now, you can multiply by 0, and that would give you the 0 vector. You can also multiply by a -1. Okay? We have negative vectors. Now, negative vectors have the opposite direction, but in this case, the magnitude is constant. Alright? So the magnitude is going to be the same, but the direction will be the opposite. And this is where, if you think about this equation here. We haven't really talked about vector addition yet, but I think you guys can get this. If I have a vector plus the negative vector, what's that going to give me? It's going to give me the 0 vector. Okay? That's going to give us a 0 vector. Alright, so that's the case we had something like that. A tug of war with 2 evenly matched teams, and they're both pulling and pulling and pulling, and no one's winning because they're evenly matched, and it's just staying still. So, any questions so far? All right. Now we get into, again, looking geometrically at a vector concept. We'll look at vector addition. Okay? Here we have 2 different vectors, v and u. And we want to look at the combined effect of those vectors on something. If they're forces, you know, one person's pulling this way and the other person's pulling this way, what's going to happen to the object that they're pulling on? Okay? A vector addition is the result of 2 or more vectors acting on an object. Right, so here you could see how we do this. We simply take vector u, and we'll draw that one first, and then from the end of that one, we do vector v. Okay? Now it's important that you always do the second one from where the last one left off. Okay? And we would call this vector right here the resultant vector. Okay? And that would be u plus v. Okay? That's a vector u plus vector v, the resultant vector. Now, basically, what we're looking at here is this result is what would actually take place. Okay? If I had two people pulling on an object here, and one was a little weaker than the other, and he's pulling this direction, and then the other one's pulling this direction, alright, you're not going to actually see both of these. You're going to see the resultant vector. Okay? Now, if they took turns, and they each pulled for, let's say, 3 seconds, you know, this guy pulls for 3 seconds, and then this guy pulls for 3 seconds, then you'll actually see the two separate vectors. Okay, and then if they pulled together for 3 seconds, the same way, you would see the resultant vector. They'd end up in the same spot. Okay? But the resultant vector is what you actually end up seeing in real life. Now, another thing that anytime you're dealing with a new type of mathematical structure, like in this case the vector, another thing you need to do is consider the different properties that you use in real numbers and ask yourself, do these still apply here? Okay? We're going to look at a number of properties like the distributive property, the associative property, those sorts of things. Alright, but one we'll look at here is the commutative property. Does it make a difference if I do u plus v or if I do v plus u? Okay? And the answer is actually no. Alright, vector addition is actually commutative. And I'll illustrate that down here. Okay? So I'll do u plus v first of all. Here's u and here's v. Okay? So what would happen if I did v first? From the same starting point, if I did v first and then I did u, I'll end up at the same point. Okay? So, I end up with the same resultant vector, u plus v, as I get when I do v plus u. Okay. And that's significant because that's not always the case. Alright, for example, if we get to matrices later on in the year, as kind of an extra, when we look at matrix multiplication, it's actually not commutative. In fact, you could actually, and often you do actually get completely different shapes of matrices. Okay, you could get one with 3 rows and 2 columns when you multiply it one way, and if you try to use the commutative property, you'll get one with 2 rows and 3 columns. Okay, so there are a lot of things out there that aren't commutative, so that's why we look at, if you're dealing with vectors, we look at, you know, are these commutative or not, okay? So let's look at just a couple of quick examples of some vectors kind of in real life. Dealing with velocities. Right. If you guys remember the opening problem we did where you were looking at the plane flying and the wind was blowing across its path. Well, here we have a situation like this. We have a 20-mile-an-hour wind when the plane would normally go 350 miles per hour. Where's the plane actually going to go? Okay. It's going to go along this resultant vector, u plus v. Now, that's important to take note of if you're the pilot and you want to end up here, okay? You can't aim right here if you're flying. You've got to aim up here. Okay? And then the wind will push you over to here. Okay? And again, that doesn't happen, like it's taking turns. We're going to fly up here and just hover until the wind pushes us over here. Okay? That all happens at once, and what you end up seeing is just the path of the airplane flying along the resultant vector. Okay? But that's something they have to take into account. Another thing with flight, particularly like when you're dealing with international flights, would be the rotation of the Earth. Even on shorter flights, just across country or something like that. If it's going to take you a couple hours to fly from one place to another, then that location is either coming towards you. If you're flying east, it's coming towards you. Or if you're flying west, it's actually running away from you as the Earth rotates. Okay? So there's a rotational vector of the Earth. It's a displacement vector of that city that you're trying to fly to that you have to take into account as well. That's why if you ever do a round-trip flight, it's rarely ever the same amount of time going there as it is coming back. Okay? And there's a lot of other factors that are come into play with that, but the rotation of the Earth is just one. In fact, that's something that before the days of rocket or GPS guided missiles and things like that, particularly, I think it was mainly in World War II when they were developing these cannons that could shoot projectiles, 20 miles. I remember one was called Big Bertha. I think it was the one that could actually shoot these things 20 miles, which in the 1940s was ridiculously long. But they were getting into distances that were so far that projectile was going to be in the air for so long that they had to take into account the rotation of the Earth. And actually the first computers built, the Mark I, and the ENIAC and the Mark IV. Was it Mark IV or Mark I? I can't remember. Anyways, ENIAC was one, and but those original computers were designed and funded mostly by the U.S. government to develop tables for their artillerymen on how to aim to get a certain distance and actually hit their targets and things. They had these elaborate mathematical tables, and the computers were able to produce them much faster than people could. But anyways, those are other examples of vectors. Another one is force, okay? Just to stand. There are opposing forces at play. Okay, you guys know every action has an equal and opposite reaction. All right? When you talk about how much you weigh, you're really talking about how much gravitational pull the Earth has on you. That's really the definition of weight. And that's why if you were on the moon, you would weigh 1/6 as much as you do on the Earth. About 1/6. because the moon is smaller, it has a smaller gravitational pull. But anyways, you have this gravitational pull downward. In order to keep yourself from just crumbling to the ground, you have to exert the same amount of force upward in order to stand, or your frame has to be able to withstand that much force. Okay? In order to actually jump, you have to produce an upward vector that's greater than the gravitational force down, okay, in order to get off the ground. But again, just a couple of simple applications here of forces, and a lot of times forces we don't even think about, okay? So, that's the overall concept of dealing with different vectors, multiplying a vector by a constant, dealing with a negative vector, and then this concept of vector addition is important. And recognizing, how is this actually happening? And actually, some of the problems we're going to do later, they have you working on, taking a series of vectors and writing an equation for that. You might have a vector like this. Okay. How could I write an equation for this vector right here? Alright, well, I'd have to write it in terms of these other vectors. Okay, and then think about also which direction the arrows are pointing and all of that. But that's something that we'll kind of learn by experience as we practice later. So let's just introduce the concept of dealing with vectors in a plane. Okay, and I start with a point, A3, 3, 5. Okay, point A is the point 3, 5, and there's a couple of terms that you need to make sure that you're familiar with here. If you have a vector, you'll notice in parentheses it looks just like a point. The notation is the same for the vector as it is for a point, okay? However, in component form for a position vector, this term position vector is key. You would write it as a vector from the origin to the point you're working with, okay? So if I have point A here, I would say from the origin to A, I have a horizontal component of 3 and a vertical component of 5. Okay? When you first learned how to graph points, really you learned it kind of as a position vector, because what were you always told to do? Well, 3 is your x-coordinate. So you move over 3 from the origin, and then you move up 5 from the origin, from there. Okay? Really, you were kind of thinking in terms of a position vector when you did that. Okay? The other way we can write a vector is in unit vector form. Okay? Now, the unit vectors in 2 dimensions are I and j. I is a vector 1, 0. And j is the vector 0, 1. So in order to write vector OA here, we would say, parentheses, we would say that equals 3i, okay, 3i plus 5j. So that's going to be our unit vector form. Now notice you can still see the components, and in component, when we're talking about components, really what we're talking about is rather than being given a direction and a magnitude directly, what we're really being given are the horizontal and vertical magnitudes. How far or how much force is being exerted this direction, how much force is being exerted up or down. Or what's the speed horizontally and the speed vertically. Okay, when you put those together, you can get a magnitude of the vector and you can get a direction. But here, when we're given it in component form or when we see it in unit vector form, you can actually see the horizontal and vertical components separate. Okay. And this is particularly useful when we're looking at applications, say with a projectile. If we have a projectile and its initial velocity vector is at a particular angle off the ground, okay, in order to really calculate things with that, we would need to figure out, hey, what's the horizontal part of that initial velocity? What's the vertical part of that initial velocity? And then we can figure out, okay, well, how long is it going to be in the air? When's it going to land over here? You know, if we're kicking a field goal in football, is it going to clear the 10-foot high goalpost? Okay? Or if we're in soccer, is it going to be lower than the 8-foot high goalpost? But looking at those horizontal and vertical components helps us to figure out things like that. Okay? Now, one other thing I want to point out, and that is some difference in notation. I always learned to write it this way, and that is one accepted way with the making it look just like a point. However, you will also see it written like this. Okay, that's how you'll see it the majority of the time in your book. Okay, so be aware of that. Those are the same thing, just two different ways of writing it. Okay, I believe IB uses the vertical way more often. However, both are acceptable. You just have to pay attention to context. All right, if you see this, is that a point or is that a vector? Okay. Make sure you pay attention to context. But I think that's why people like to use this, is because then you don't have the confusion there. But yes, Charlie?
What about the two cubes?
Like this?
Yeah. Because I feel like that's what, like, I've seen most.
You've seen that before?
Like, yeah, most of the time.
Okay. What context did you? Was that in math or was that in physics?
Who saw that last time?
You saw that last year?
Yes.
Okay. So, I mean, it means the same as well. Honestly, I haven't used that really ever. I mean, I've seen it, but I've never really used it. So, honestly, it's partly just what you're familiar with, where you're from, kind of. Different parts of the world use different ones, or sometimes even different fields will use different notation as a preference. But the nice thing with IB is any acceptable or any valid one will be acceptable. All right. So Now, getting back to something we mentioned earlier, we talked about equal vectors. Equal vectors here are going to have equal components. And that's kind of a simple concept. I mean, it makes sense that if I have a vector 3, 5, then 3, 5 is going to be equal to it. But equal vectors will have equal components. The last thing is just how do we get a vector if we have 2 points? And we'll revisit this a little bit later and work with it even more, but I did want to mention it here. Here we have vector AB. AB is a position vector of B relative to A. And here's the language that you got to be familiar with. The position vector of B relative to A. What this is saying, and you may not see the actual name of it when you see this. They'll just say, find the position vector B relative to A. When they're saying relative to A, normally our position vector is relative to the origin. But when they say relative to A, they're saying, hey, where is B compared to where A is? And B is going to be the ending point. A is going to be your starting point. All right, so you see here I have 2 points. A is the point 62. B is the point 13. So if we're trying to find, hey, where is AB, or where is B in relation to A? Well, let's look horizontally first. A is over here at 6, B is at 1. So where is B in relation to A, horizontally? If A is at 6 and B is at 1, it's 5 units to the left, right? Okay, and on our x-axis, when we go to the left, that's negative. So we would say that's a negative 5. Okay? So if we're finding vector AB, we would have negative 5. And then vertically, how would we get from A to B?
1.
Yeah, we have to go up 1. All right, so that would be our vector negative 5, 1. So, what if we had it the other way, vector BA? No. There we go. Okay, it's going to be the opposite, right? So BA is the same as a negative AB, right? It's the same magnitude but opposite direction, so that'll take us positive 5, negative 1. Okay? All right. Now, the remainder of our time, what I want to do is give you guys the opportunity just to get some hands-on work with these concepts. I know we've touched on a lot of concepts today. In fact, we've covered the first 3 sections of chapter 12 today. And tomorrow we're going to cover D, E, and F. So we're going to cover 3 more sections tomorrow. But I recognize that this is not totally brand new. But hopefully what you're seeing are some things that maybe you forget that you need to go back and review some more. Obviously, we're bringing things to light, kind of laying a groundwork for later on. But this should open up some areas. Maybe there's something that we talked about here that you didn't cover last year, or you totally forget. And this is the time for us to get this firmly into our minds, okay? Some of what we're going to do may seem a little bit tedious, okay? The fact of the matter is, though, you've really got to know this stuff well in order to do the more advanced applications of it, okay? And we are hitting a number of sections quickly here at the beginning, but we're gonna slow down, once we get to the brand new stuff, and really take our time to learn how all of this plays together, okay? So, we're gonna use the remainder of our time to work on these. There's a number of different problems on different pages that we're gonna work on. I'm gonna have you guys find spots at the board to work on these, okay? So you can work with somebody, but I want everyone up and moving and participating so that we can make sure we get this all under control.